Hi, I'm Brandy Heflin. I'm a personalized physics instructor and I help high school and college students feel confident and successful in learning physics. Two of my clients recently brought to session a really unique kind of problem, and both of them had the same difficulty with this problem. One is somebody who's preparing for the AP Physics C mechanics exam, and the other is a college student who's on trimesters and so has just begun mechanics. And the kind of problem they both had difficulty with is something called a modified Atwood's machine. A modified Atwood's machine is a pair of blocks connected by a string which passes over a pulley. And one of the blocks could be hanging straight down while the other block is resting on a table, or in the problem we have today, we have two blocks that are both resting on inclined planes that are the sides of a wedge. And the difficulty that both of my students had was with the idea of systems thinking. They had not been shown this approach for solving this kind of problem by their instructors. So for this modified Atwood's machine, you can see that we have the 1.6 kilogram block A resting on a 51-degree incline that makes up one part of the wedge, and then we have 8 kilogram block B resting on a 31-degree incline that makes up the right half of the wedge. And we are also told that the coefficient of kinetic friction equals 0.30, and that's between both block and surface pairs. So this systems thinking is it's choosing a system cleverly so that we can make solving the problem easier by reducing, or even in some cases eliminating, some of the variables we might need to solve for. So let me show you. I like to draw a circle around the boundary of my system. For a problem like this, it's going to include the blocks and the string, but not the pulley. And so now, with tension inside the system, it's going to reduce the number of forces we need to deal with. And here's why it makes sense to do it this way. With the blocks being tied together, if block B moves down its ramp, block A is going to move up its ramp. And if block A moves down its ramp, block B is going to move up its ramp. And so because these two are tied together and are going to have to move together, we also know that they will have the same velocity at any point and they will have the same acceleration. So before I go constructing my force diagrams for the two blocks, I am going to go ahead and specify that I think it's going to be the component of block B's weight that's parallel to the ramp that is going to pull the whole system. So I'm going to guess that block B is going to move down its ramp while block A moves up. So I will go ahead and label that my positive x direction is like this for block B, and that my positive x direction is like that for block A. So some force diagrams. We only need to deal with the forces now that are interactions with objects external to our system. So our blocks interact with the earth and our blocks interact with the surface, both with friction and a normal force. So I'll go ahead and give us a force of gravity on block A. There will be a normal force on block A that points up and to the left, perpendicular to the 51-degree incline. And then there's going to be a force of friction on A down the ramp. Because again, if I think block A is moving up the ramp, friction is going to oppose that motion. And for block B, we will have its weight. There will be a normal force on block B perpendicular to the 31-degree incline. And then the force of friction on B is going to point up its ramp because I think block B is going to move down its ramp. So to set up my Newton's second law equation of net force equals ma, I'm going to specify that I'm dealing with the net force in the x direction for this system equals the mass of the system times the x direction acceleration of the system. And let me go ahead and review for you quickly the components of forces and some of the other equations that we're going to need, because you see on here normal force and friction, and I've talked about components of the weight. So I do anticipate that you would have learned previously that the x component, or the parallel to the ramp component for a mass on an incline, is equal to mg sine theta, and the y component will be mg cosine theta. And we know that because there's no acceleration perpendicular to the ramp, that the net force in that direction for either one of them, either one of the blocks, must be 0. So that means normal force will be equal to Fgy. And the last relationship we need is that the force of friction will be equal to mu, the coefficient of friction, multiplied by the normal force. So now we're ready to set up our big Newton's second law equation for our system. So we're going to have the x component of block B's weight that is going to pull the whole system down its ramp. And then we can visually trace back up and realize that the force of friction on block B is opposing that. And then we can trace up and over the pulley, and we can see that we will have the x component of block A's weight pulling back down the ramp. And we will also have the friction on block A pulling back down the ramp. And then the mass of our system is going to be mass of A plus mass of B, because both blocks are tied together and moving together and will have the same acceleration. I'm going to go ahead and let the 31 degrees, I'm going to call it theta B, and the 51 degrees I'm going to call theta A when I start plugging in these components. So according to the review we just did, FGBX will be MBG times the sine of theta B, and we will subtract the whole term for force of friction on B, which will be mu K, times the normal force on B, which we said is the y component of B's weight, so MBG cosine of theta B. And then we will need to subtract block A's x component of the weight. There we go. Sorry, I got a little caught up and excited about writing all of those B's, and we're switching to block A now. And then we'll need to also subtract the friction force for block A. So MAG cos theta multiplied by the coefficient of friction. And that's going to be equal to the sum of our two masses times the acceleration. And now we're ready to substitute. So we'll take our 8.0 times 9.8 times the sine of 31 degrees minus 0.3 times 8.0. And I know I'm writing a little bit tight and small. It's because there's a lot we've got to fit in here. So multiplied by the cosine of our 31 degrees, minus 1.6 times 9.8. It's not going to look quite that pretty. Oh well. Times the sine of the 51 degrees, minus 0.3 times 1.6 times 9.8 times the cosine of the 51 degrees, and that's going to be equal to the quantity of 1.6 plus 8.0 and quantity multiplied by the acceleration. So ordinarily, I would just go straight to my calculator and enter all of that and spit out an answer for the acceleration, but to make sure that you can follow along with each term, I'm going to go ahead and evaluate each term, each little set of calculations, and show you what I get. So my 8.0 times 9.8 times the sine of 31 degrees, I get as 40.379. And my 0.3 times 8.0 times 9.8 times the cosine of 31 degrees, I get to be 20.161. And my 1.6 times 9.8 times the sine of 51 degrees, I get to be 12.186. And my 0.3 times 1.6 times 9.8 times the cosine of 51 degrees, I get to be 2.96. Oops, that did not turn out that pretty. There we go. And that's going to be equal to a total of 9.6 times A. So when I combine all of those terms on the left side of the equation, I get 5.072 equals my 9.6A. So my acceleration ends up being 0.53 meters per second squared. So a quick check. I did get a positive value of the acceleration, which means that I chose the positive direction for my forces to be correct. If I had been wrong and it were block A that were pulling the system, I would have ended up getting a negative value for my acceleration. I do want to go ahead and show you how to find the tension as well, because you will almost certainly in a problem like this be asked to find the tension in the string, but I do need to move to a new slide. So to solve for tension, we're going to go from treating our whole system as the pair of blocks that are tied together and slide together to handling one block or the other at a time. So let's start with a force diagram for block A. We'll have the force of gravity on block A straight down. We will have a frictional force on block A that is parallel to the ramp and down the ramp. We'll have a normal force on block A that is perpendicular to its ramp, which is up and to the left. And then we will have a tension force on block A that is up and to the right and also happens to be parallel to the ramp. And we'll go ahead and do our force diagram for block B as well. So again, we'll have its gravitational force is straight down. The normal force on this block will be up and to the right. The frictional force on block B will be up and to the left because it's going to be parallel to block B's ramp. Block B, remember, is going to be moving down its ramp, so friction is going to be up the ramp to oppose that. And whenever I have two forces that are pointing in the same direction, I like to draw those vectors tail to tip on my force diagram. So I'll go ahead and put my tension force out there at the end of the frictional force on block B. So I will show you both ways of doing this. It doesn't matter which block you choose. We will start with block A. So when we now complete our Newton's second law analysis on block A, we're going to notice that The tension force is the positive x direction force that is making block A accelerate, and then the frictional force on A and the component of A's weight down the ramp are opposing that. So I can let tension be my positive force, and then I can subtract the other two forces. And then set that equal to the mass of block A times the acceleration. So we've already calculated previously everything here except for, of course, the mass of block A multiplied by the acceleration. So before I go ahead and solve and start plugging things in, I'm going to add both the force of friction and A's weight component to the right side so that I have isolated my tension force. And recall from the first part of our problem that the acceleration of our blocks is 0.53 meters per second squared. And we previously found that the force of friction on block A was 2.96 newtons. And we previously found that the component of A's weight that is parallel to the ramp is 12.186 newtons. So 1.6 times 0.53 gives me 0.848 plus our 2.96 plus 12.186, and we're left here at the end with the force of tension is equal to 15.99 newtons. So I like using block A for a problem like this because the quantity that I'm solving for is already my positive direction force for block A, and then the other forces are the negative direction forces. So the mathematics works out really simply in order to isolate the thing I want to solve for. What you're going to see happen with block B is that we're going to have we'll have to move tension from the left side to the right side, and then we'll have to move MA from the right side to the left side. And even I still make algebra mistakes once in a while, and having things going both ways in the equation sometimes trips me up. And so I prefer using block A because the things that I had to move to isolate the variable I'm solving for were all going the same direction. So to use block B for this, we're going to note that it's the component of B's weight down the ramp. That's the positive direction force for B. And then the friction on block B is opposing that, and so is the tension. And that's going to be equal to the mass of B times the acceleration A. And so to help make this algebra really clear, I'm going to go ahead and change colors. So I'm going to add the force of tension to both sides, and then I'm going to have to subtract the mass of B times the acceleration from both sides as well. So on the right side, I'm now left with just the force of tension, and I'm going to go ahead and write it as the left side of my equation, since that's what I'm solving for. And then that other side remains FGBX minus the force of friction on B, but now it's going to be minus MB times A. So we've previously solved for the component of B's weight, and we've solved for friction. So the component of B's weight that's down the ramp is 40.379, and the frictional force on B is 20.161. And then we will have to take our 8.0 kilograms multiplied by our 0.53 meters per second squared. And I get for that last term, 4.24. Sorry, I had to find it on my notes over here. And so I get a final answer of 15.98 newtons. And the reason I got something that's just a little bit different, and actually, you know, I want to write this just a little bit differently. The reason I got something that's a little bit different than what I got before, so the decimal, that final decimal place is off by 1, is just because of how I've rounded things while working the whole problem. If I went back and redid the whole problem and kept more decimal places the whole way through before rounding anything, including keeping more decimal places on my acceleration, or maybe keeping 5 or 6 places for each of those values of the forces that I've used, by the time I get to the end of a segment like this, I would see that that hundredths place is going to align a lot better. Thank you for joining me today. I hope that you found this explanation of systems thinking when used to solve a modified Atwood's machine helpful. If you would like to connect with me further, you can reach me at brandyheflinphysics@gmail.com. I am offering complimentary 60-minute family discovery sessions where you can get a chance to work with me and we can explore whether working together in a more long-term tutoring relationship is right for you. I'm currently taking problem requests. If you have something that you're working on that you need some help with, whether it's a concept you need clarified or perhaps you know, something from your homework that's giving you some trouble, you can reach me at physicsproblemrequests@gmail.com. You can also find me on my website, brandyheflin.com, and on Facebook at Physics Tutor Brandy. I love physics and I love helping you. Until next time.